makes me smile just to be alive and to know that I'm your child. Mercy is new every morning. You pursue me. You never let me.
The second law of thermodynamics is a really big deal in science. Its effects impact every field of study, every aspect of our existence. It is inescapable and pervasive. Yet, inexplicably, the principle behind it is misunderstood by nearly everyone, including most scientists. Now, many have learned a definition or two, but if you want to understand how the universe works, you need to go deeper than merely defining the second law of thermodynamics. You need to get the concept, the principle. When you do, you'll begin to understand everything in a whole new light. For the next few minutes, I want to explain this principle, or principles, that will make such a difference in your thinking. To begin with, the second law of thermodynamics is about much more than thermodynamics. Oh yes, it began with thermodynamics. Rudolf Clausius formalized the law in 1851 with an understanding of how heat dissipates as a result of any event. But within 20 years, Ludwig Boltzmann discovered that the principle behind it was the behavior of statistical probabilities, and not just regarding energy, but everything. It's amazing how many scientists have not gotten the memo, but it is not just about energy. The law goes by many other names. It's been called the law of increasing entropy, the law of decay, the law of spontaneous randomization, the law of probability gradients, and many others. The basic principle is this: arrangements tend toward greater randomization over time. This means that as time goes forward, everything winds down, wears out, rusts, grows old, decays, degrades, disperses, diffuses, dissipates, and generally gets mixed up. In fact, early thermodynamicists have described this thing called entropy as mixed-upness. And within any defined system, barring intervention that is, entropy will always increase. Spontaneous change toward randomness can be slowed down, but never completely stopped. The Bible put it this way 3,000 years ago: the universe shall wear out like a garment. So far, so good. But there is much more to understand than that. So here are the big ideas to get: arrangement, arrow of time, entropy, constraints, defining the system, and entropy transfer mechanisms. As I've studied these things over the years, I find the second law to be very fascinating and exciting, even astonishing. But before I can get you to that place, I need to teach you some principles that took me a long time to uncover. Going through this may seem very dry, but I assure you that if you will hang with me, very exciting conclusions will follow, okay? Number 1, arrangement. The second law is all about arrangement. Arrangements of anything, of energy, of matter, even of information, anything. More to the point, it's about statistical, probabilistic arrangements of large numbers of things. The law doesn't tell us much about small ensembles of, say, 5 or 6 items, because dumb luck can arrange small numbers like that pretty much any which way, given enough trials. But probabilities become much more predictable as the numbers go up. Flip a coin 10 times and not much would surprise us. Flip it 100 or 1,000 times and we expect the percentages to get closer and closer to that 50-50 ratio. This is basically the law of large numbers. It's part of the math of statistics. When you think about it, large numbers are all around us. How many air molecules are in your lungs right now? How many grains of sand on the beach? How many electronic bits in an internet transmission? How many microscopic parts make up your body? Do you see what I mean? Some of these arrangements are very random, while other arrangements are very particularly specified for a purpose or function. It's that idea of specified versus random that we're talking about. Some folks use the words order versus disorder here, but simple patterns are mistakenly thought of by some to be order, and that can make the word misleading. I prefer to speak of specified arrangements, which carries the idea of purpose in an unlikely arrangement. That purpose can be derived from a specifier or agent, but it can also be derived from that arrangement's coherent functionality. To illustrate, the text for Hamlet does not appear to have any pattern of order to an outsider, but it's an extraordinarily improbable arrangement of letters with the purpose of communicating a detailed story. Thus, it is a specified arrangement. For our purposes, any arrangement that does not convey the intended story would be random in this dichotomy. So again, it's the idea of specified versus random that we are talking about. Or we might even say purpose versus purposelessness. Number 2, arrow of time. The second law is all about the directional nature of time. Time moving forward is characterized by spontaneous, that is by itself, randomization of arrangements. Time moving backwards would be characterized by randomness, reversing and ordering itself. But in fact, time goes one direction, forward. Think of a glass dropping on the floor and shattering. If you watch that video forwards and backwards, it's quite easy to tell which direction is reality. That's because of the arrow of time. When a thing or part of a thing becomes more random, it's following the nature of time itself. Time randomizes stuff. It doesn't specify or order stuff. The second law is why a perpetual motion machine is impossible. Time goes one way. It winds down and runs out, sometimes slowly, sometimes quickly, but always the same direction, towards randomness. Number 3, entropy. The earliest definitions of the second law of thermodynamics were in terms of entropy, in other words, mixed-upness or randomness. For example, look at this definition. In an isolated system, total entropy must increase over time. Entropy is supposed to quantify this randomness, but how might this be done? Well, at first it was the arrangement of energy that Clausius was trying to describe, and he thought in terms of the heat that dissipates into randomness during an energy process. So mathematically, he quantified entropy increases by taking the total heat energy lost in a process, measured in joules, divided by the temperature in degrees Kelvin, and the wasted heat per degree then became the definition of entropy increase. However, within 20 years, Boltzmann was seeking ways to take a more comprehensive look at randomization. He took a statistical approach in experimenting with the random behavior of gas molecules. His conclusion was to define absolute entropy mathematically as the sum of the log of the probability of each possible arrangement in a system. To his surprise, he found that by multiplying this result by a constant, which is the now famous Boltzmann constant, he could convert his number to perfectly match the heat number of the Clausius formula when dealing with thermal entropy. So the exact same result by statistical mechanics instead of by thermodynamics. Actually, quite a discovery. And that wasn't the end of it. Less than a century later, Claude Shannon applied the same math to the arrangement of information bits in storing and transmitting messages, minus the Boltzmann constant, of course, giving us, you guessed it, informational entropy. So the bottom line is that entropy is not about heat loss, but about probabilistic statistical arrangements. Notice that the early definition of the second law was framed in terms of entropy, which is fine when you're only dealing with energy, but a more comprehensive definition was needed for the generalized second law. So the more accurate definition is stated this way. In an isolated system, the direction of spontaneous change is from an arrangement of lower probability towards an arrangement of higher probability. Since there are more ways to be randomly arranged than there are arrangements that are functional or specified, greater randomness is going to be much more probable, except in those rare cases where an intervention temporarily alters the probabilities, but generally arrangements follow the high probability of randomness. Despite the upgraded definition for the second law, entropy remains an important concept in our understanding. You see, entropy is a relational property, like temperature, not an intrinsic property like mass. Relational properties are characterized by spatial considerations. In other words, entropy has location. This will be important later on when we talk about transferring entropy. It just can't disappear, but it can be transferred. I mention this because there are ignorant scientists who mistakenly think that a local reduction in entropy can simply be compensated for somewhere else in the universe. But transfer is very different from unrelated compensation. Transfer involves physically moving the property with a causal chain of connection. Constraints. Arrangements randomize over time, but it must be understood that pure randomness probably does not exist. Randomization is slowed, guided, and bounded by physical constraints that come from physical properties and natural laws. Such constraints on randomization are the rule, not the exception. In fact, were it not for these constraints, the universe would probably go poof in a dissipating vapor, but thankfully most randomization occurs slowly. Constraints take many forms and act in different ways. When we blow up a balloon, the compressed air inside is improbably compressed, while the uncompressed air in the surroundings constitute a more probable arrangement. Hence, the law gives the compressed air inside the tendency to escape and mix with the surroundings. If we pinch the neck of the balloon, we constrain that tendency. If we release our fingers, a portion of the constraint is removed and the air flows rapidly through the neck. But if instead we remove the constraint against the entropy increase by popping the balloon with a pin, well, we get an idea of just how fast the second law of thermodynamics can work. But some constraints act differently. Consider dripping an ink droplet into the ocean. We all know what will happen to the ink molecules. They disperse throughout the ocean, although not as quickly as the popped balloon. That's because of the viscosity inherent in water. So what if the ocean was thick syrup? Our intuition tells us that the ink would spread through the mixture much more slowly because of the higher constraint of a higher viscosity fluid. As a final part to this thought experiment, what if the ocean was now made of oil? Yes, the ink would randomize very slowly, but it would do something else too. The random ink would drift downwards since water is heavier than oil. The randomization would take a different form altogether, and so it goes with almost any example of entropy increase. Randomization will always occur everywhere in the universe, but always within the physical constraints that may be present. Arrangements spontaneously follow the probabilities towards randomness within constraints. Defining the system. I'm sure you noticed that both the old and new definitions of the second law of thermodynamics includes a caveat, quote, in an isolated system, unquote. When we talk about increasing entropy, it's only reasonable to ask, increasing what number? And measured within what limits? The mention of a system is there for a reason. The hypothetical isolated system gives us a mental construct for understanding the way the second law measures entropy and the way it performs. We need this mental construct in order to frame the definition, in order for the idea of an increase to even make sense. Certainly the entire universe might be thought of as our system, but we could just as easily consider the solar system or the Earth-Sun system, or maybe just the Earth's biosphere, or even the room within which we are performing our experiments. But please understand this point. The definition of the second law conveys a principle. Seek principles, not loopholes. Parsing words will not help desperate evolutionists escape this foundational law of science. Sadly, many brilliant scientists seek to dodge the law with exactly such methods, suggesting that an open system which allows sunlight in is not subject to this law of science at all. Nothing could be further from the truth. Increasing randomness applies everywhere to every part of every system, open or isolated. It just can't be defined clearly for an open system, but the principle does not go away just because biologists want it to. It is a principle, people, not a loophole. And the principle driving the law works everywhere without exception. Entropy transfer mechanisms, ETMs. So having said that, why are there such incredible ordered systems on our planet? Somehow only on Earth have we arrived at a place with human brains and computers and spacecraft. Living things are the most remarkable arrangements of matter, energy, and information in the universe. Every living cell is like an intricate, integrated city with each part performing its function on cue. How can such low probability, low entropy things even exist? Never mind why. The rest of the universe exhibits endless increasing entropy without exception. So why is the Earth so different? The second law cannot be broken, but it seems to be in living things. So what's going on? The answer lies not in a loophole, but in the nature of the law itself, in arrangement probabilities. By intervening and altering local probabilities, local entropy can be transferred into the surroundings. This intervention can be performed by means of something Peter Atkins called mechanisms, Andy McIntosh called machines, Granville Sewell called X-entropy, and I call entropy transfer mechanisms, or ETMs. Not merely an input of energy, but a mechanism to harness that energy to dramatically increase the probability of a specified arrangement in a locality, while at the same time dumping excess entropy into the surroundings. These ETMs make use of the law itself through probability modification and thereby transfer entropy out of a locality at the expense of randomizing the surroundings. The law remains intact, and sophisticated organization within a locality can be the result. So how about some examples? Consider the photosynthesis mechanism inside plants. Sunlight alone would dry up and destroy plants, but the photosynthesis ETM actually builds them. Plants use chlorophyll to harness very random, even damaging sunlight to manufacture carbohydrates and oxygen from carbon dioxide and water. This is just one example of an ETM, and living things have billions of them in every cell. Life is built with very long molecules called proteins, manufactured with exact amino acid sequences, and every cell has stunning molecular machines that serve as ETMs to perform mechanical operations to build these structures and fold them with precision. A collection of ETMs use outside energy to actually build a human being from a zygote in the womb. Causing sophisticated specified arrangements to become temporarily highly probable is the only way that life can exist in a universe that is decaying. And these entropy transfer mechanisms are the only thing between us and the dust of the earth. To better grasp the concept of an ETM, it might be helpful to think of an ETM as a factory. Factories build things, creating order and purpose. The process of doing so consumes a lot of energy and lets out smoke and heat from the smokestack as well as garbage out the back door. Nevertheless, remarkable devices can be built in factories that can't be obtained without them. So it is with ETMs and living things. In short, ETMs build things. But where do ETMs come from? What mechanism builds them? And by the way, ETMs are also subject to the second law. ETMs in factories eventually wear out too. That's exactly why life dies and must be replaced routinely by ETMs that build other ETMs. We know in our experience with biology that ETMs are sourced in information. Okay, so where does the information come from, since information itself is subject to the second law? It's copied by other ETMs from previous generations, but in the end, all information has intelligent mind as its ultimate source, and intelligent mind is the ultimate ETM, the controller of probabilities. So what about evolution? It's not hard to see that the second law of thermodynamics, properly understood, devastates the entire idea of both chemical and biological evolution at the most basic possible level. It makes every other argument moot. But the human biases of evolutionists seem to block their understanding, since these are very smart people. Their primary defense is to excuse their theory by virtue of the fact that the Earth is an open system. That's it. That's all they have. Richard Dawkins has stated that the second law can be disregarded simply because of the sun. The energy input of sunlight is supposed to invalidate the application of the laws of science to biology. You can almost hear him shout, "Loophole! Loophole!" Evolutionists claim that sunlight is the magic ingredient that makes entropy decrease possible, but it's simply not true. Sunlight is actually very random, and what's needed is the polar opposite of random, which is specification. To explain the open system fallacy, Granville-Sewell has offered the idea of two hypothetical scenarios as another thought experiment. In the first scenario, a powerful tornado strikes a house and turns it into a pile of rubble. In the second scenario, a second tornado of equal force strikes the pile of rubble and builds a perfect house. So both scenarios are open systems with an ample supply of energy, but clearly the first scenario is reality and the second scenario is fantasy. Tornadoes don't build houses. In the second scenario, an energy supply is not the solution to the problem. Energy is the problem. Random begets random, and in our heart of hearts we all know that intuitively, yet common sense tells us that carpenters could conceivably do it. Carpenters might take the pile of rubble and rebuild that house, using no more energy than the tornado had. That's because carpenters constitute an entropy transfer mechanism. They are the ETM that alters the probabilities. Their presence makes a perfect house much more probable than the pile of materials, and voila. As I said, intelligent mind is the ultimate ETM. Intelligence has the ability to improve the probability of specified functional arrangements like nothing else can. But here's the problem. Information runs the show in biology. The source of that information is the central question. While there are many ETMs in living things that build biological parts, we don't see any kind of ETM for either originating or building up the genome. Only an ETM can transfer entropy out of a locality, so what mechanism builds the information encoded in DNA-based sequences? What ETM do evolutionists propose for that? DNA is the most fantastically low entropy zone in the universe. The book of life, as Ray Comfort has termed it, is the farthest end of the spectrum from random. So after all that I've just explained about a foundational, inescapable law of science, my question for materialist evolutionists is as inescapable as the second law of thermodynamics. What ETM can you imagine has the capability to write the instruction book of life in DNA code? Then after a while comes the only answer they can conjure up.
Mutations! Random mutations generated and continue to build the information sequences in DNA.
Oops, I say. Random is not an ETM. Sorry, but it is not, and never could be. Random is the polar opposite of an ETM. It does not make a functional genome more probable, it makes it far less probable. Random is what ETMs are built to undo, not to embrace. Random mutations most certainly degrade the genome, never sophisticate it. Genetic science has actually verified this ongoing decline, as John Sanford explains in his book, Genetic Entropy. The broad human genome is in fact degrading, not advancing, according to the data. The second law is working exactly as expected. Michael Behe's latest book, Darwin Devolves, goes a step further by bringing out the latest molecular level findings. Genomes are devolving, not evolving. Dr. Granville-Sewell, champion of the second law, said of Michael Behe's book, exactly what the math predicted. Then comes the evolutionist's last gasp.
But random mutations are not really random. They are directed by natural selection.
So, they always say. Oops again, I say. Natural selection is a constraint on random, but random within constraints is still random. Natural selection kills and culls. It does not build anything. Killing the weak cannot reduce entropy, only slow the increase in it. Random begets random. I don't think most people grasp just how much more probable randomness is in contrast with the genome of life. Living things represent the rarest arrangement of atoms and parts in the universe. Trillions upon trillions of parts working in integrated functionality. There are so many more ways to arrange those parts in a lifeless way than there are living ways. How many more? Mathematical estimates are 10 to the 40,000th power more ways. Keep in mind that 10 to the 80th power is the number of atoms in the known universe, yet there are 10 to the 40,000th power possible arrangements that can't work. That's a 1 with 40,000 zeros after it. To say that random mutations are less likely to write code than to damage the code is a vast understatement. Fantastically improbable, as molecular biologist Douglas Axe put it. Let's take this up to the next level. I told you at the outset that the generalized second law of thermodynamics impacts every aspect of our existence. Let me show you what I mean. The neo-Darwinian model of evolution consists of three things together. Natural selection, operating on random mutations over millions of years. How does the second law of thermodynamics inform us about each of those three components? Let's start with natural selection. In Origin of Species, Darwin hung his entire argument on the false premise that natural selection preserves, with a P, preserves members of a population having the most effective traits for survival and reproduction. In today's world, that would mean the better arrangements of nucleobases in DNA. So in other words, Darwinists think that natural selection preserves the best genomes. No, that's not at all what natural selection does. It kills weak things. It doesn't save fit ones. We have just learned how the second law is relentless. Entropy increases. True preservatives are impossible under the second law. Now, yes, I know that we often call things preservatives that merely slow down the randomness, like Grandma's strawberry preserves. Her jam may last longer than fresh strawberries, but even Grandma's preserves eventually go bad. Likewise, freezing or formaldehyde and the like can only slow down degradation, never stop it. So when Darwin states in his book title, quote, "The Preservation of Favored Races," unquote, he is making an objectively false statement. Natural selection works by causing death, not stopping it. It works by blocking reproduction, not making it happen. It is a culling mechanism, not a preserving mechanism. Natural selection might constrain the overall population decay, but it cannot stop it, and it certainly cannot reverse it. Next up, random mutations. Evolutionists claim that evolution is a fact. Is this true? Well, if they mean that change over time is true, then yes, change is true. If they mean that natural selection is true, then yes, it is true that weak things die. However, when they speak of random mutations producing coherent genetic instructions, that is patently absurd, and it's in direct violation of the inescapable law of science that we've been discussing. The random mutation part of the evolution model does not even qualify as a hypothesis, let alone a theory. Actually, scientific law says that it is a lie. Entropy must increase. Genetics was in its infancy when Darwin wrote Origin of Species, but he summarized the idea of hereditary traits with phrases like random variation or descent with modification. He was unable to elaborate on the mechanism of that modification in his day, but evolutionists now speak of random mutations as the only available vehicle for writing and modifying the genetic code. We've already spoken of how the second law emphatically blocks the spontaneous origin of new information, and how randomness always degrades information rather than ever building it. Increasing randomness cannot encode symbolic sequences that spell out instructions in DNA, nor can it ever know how to conform to the right syntax and grammar that would make any coherent sense, and precisely because randomness does the reverse. In what universe could dumping out a lottery barrel full of letters ever write the complete works of Shakespeare? But I assure you the human genome is far more vast, complex, coherent, and integrated than Shakespeare ever was. So the second law defeats spontaneous origin of information, and even if a small segment of recognizable coherent base sequences ever fell into place against all the odds, time would promptly randomize it all over again. So are beneficial mutations ever plausible? As we've shown, mutations always break genes and never build them. But yes, actually, sometimes breaking an existing gene can be situationally beneficial to an organism. The sickle cell mutation is an example in which gene damage stops malaria. Some bacterial mutations result in resistance to antibiotics and fall into this category as well. Mutations are always informational damage, even if a desirable outcome is the rare result. Think of Hitler's car in a crash. Now that is beneficial damage, but not very helpful to the car. So can mutations be beneficial? Maybe. Too trivial to notice? Sure. Informationally productive? Never. This is what the second law tells us, and this is exactly what we find. Yet it is not just informational entropy that's in play, it's also conventional thermal entropy that comes to bear upon the molecules themselves. DNA and protein molecules are examples of polymers, extraordinarily long chains of smaller molecules. Most proteins consist of hundreds of amino acids, and a single DNA molecule consists of 3 billion, with a B, nucleotide pairs. The molecules of life are unlike anything else. They are huge, and they are delicate. Big molecules like this have a high level of what is called Gibbs free energy. The chemistry of this means that they tend to want to break down into their constituent molecules that have lower free energy and higher entropy. In other words, these big molecules naturally break down rather than build up in accordance with the second law. Synthetic chemists like James Tour will tell you that building these complex molecules of life is enormously difficult, even in high-tech laboratories. Polymers must be built by ETMs. They don't just fall into place, and left to themselves, they break apart over time. So let's review our case thus far. Increasing entropy blocks natural selection from preserving anything. Increasing entropy blocks the origination and subsequent building up of genetic instructions. But increasing entropy also blocks the building of the huge molecules that carry those instructions. Using the second law, there remains one more thing to examine. Millions of years. Mutations are said to work over millions and millions, even billions of years. Studying arrangements of biological systems that would be considered laughable if they materialized rapidly are considered plausible when stretched very gradually over deep time. Nobel laureate George Wald famously said the following regarding evolution: "Given enough time, it will almost certainly happen at least once. Time is, in fact, the hero of the plot. Given so much time, the impossible becomes possible, the possible probable, and the probable virtually certain. One has only to wait. Time itself performs the miracles." This statement is stunning because it comes from a brilliant scientist whom one would think would have heard about the second law of thermodynamics and would have heard about the arrow of time that is a central tenet of that inescapable law. Time is not the hero of the plot. Time is the enemy of the plot. The thing that Wald and so many evolutionists imagine driving evolution is the very thing that demolishes it. And by the way, even if time worked in their favor, which it doesn't, billions of years is not nearly enough. One simply has to run the numbers on the probabilities of arranging the simplest of proteins to find that there are not enough resources in the history of the universe, not enough nanoseconds, and not enough atoms to provide enough trials to ever come up with even that one simple protein, provided you could overcome all the other thermodynamic problems of building them. The arrow of time crushes millions of years. Now there's one more problem with the millions of years as it relates to the second law, and that is the rate of biomolecular decay in the age of the Earth. This will be controversial even among intelligent design proponents, so I want to remind you that we already have an irrefutable case against evolution without going further. But I can't in good conscience hold this back, so bear with me. I'm not telling you what to conclude or believe, mind you, only what the evidence shows. I report, you decide, as the saying goes. The same principles that block the assembly of polymers inexorably dismantles them. The role of entropy in chemical reactions is well studied. Reaction rates and direction can be calculated. As I said previously, very large, intricate molecules like proteins and DNA tend to have high free energy, and their decomposed products tend to have lower free energy. This difference drives the reactions toward the breakup of molecules instead of retaining the original. Other factors can be introduced that speed up these reactions even more, such as heat, pH, and the presence of water, oxygen, or other chemicals. For example, digestion speeds up the decomposition of proteins enormously by the presence of acids, microbes, and enzymes. That breakdown can begin to happen in mere minutes, basically by removing constraints against the second law of thermodynamics, not unlike popping that balloon we talked about. Fast breakdown of these huge molecules happens naturally. Constraining the process is difficult. Tissue preservation science is an exercise in futility, but it is also well studied. Experts have tried various ways to suspend chemical decay. Experiments involve cross-linking, freezing, drying, isolating, and creative ideas like Maillard reactions and iron-mediated cross-linking. But when the free energy differential between reactants and products is substantial, we are right up against the second law, because high free energy represents a low probability arrangement. Low free energy is a high probability arrangement. Eventually, with the passage of time, that probability gradient brings inevitable molecular breakdown. Brian Thomas, with a PhD in paleobiochemistry, points out that the chemistry calculations under hypothetically perfect conditions give us an upper age limit of about 900,000 years for the decay of bone collagen held at 10 degrees Celsius. Collagen, being water-resistant, thick, and stringy, should last longer than other original proteins. Most will have a much shorter shelf life, but substantial experimentation under likely conditions suggests a more likely upper limit of only 10 to 30,000 years for these polymers. These are maximum time frames before such molecules disintegrate. What was that I said earlier? Oh yes, the second law is inescapable. But in 2005, the world was shocked when Mary Schweitzer discovered unfossilized original tissue inside a fossilized T-Rex dinosaur femur in Montana. Dozens of discoveries of these huge and delicate biomolecules amid fossils have followed. In 2014, original protein and chitin molecules were discovered in early Cambrian marine worm tubules, presumed to be more than 500 million years old. In January of 2020, molecules that reacted exactly like DNA were detected inside visible nuclei within visible cells in remains of original cartilage of a duck-billed dinosaur. To date, over 100 articles have appeared in peer-reviewed journals covering discoveries of such original biomolecules within deep strata. It seems that more come in with each passing month. How can so much short-lived material persist throughout so many fossils? All this clearly goes against the grain. The majority of PhD scientists are entrenched in a deep time paradigm. Even so, it should not be forgotten that at least 250 intelligent PhD scientists are convinced that the Earth is much younger. And it's an important point that absent historical documentation, age is an inference, not a measurable property. Age is always inferred from a series of assumptions in combination with the second law, and with observations about present decay rates and present decayed states. The resulting calculation is not knowledge, but inference. Did you know that the law of increasing entropy allows us to make use of hundreds of ongoing processes as natural clocks? Yet the ages rendered from these natural clocks are all over the board. Rarely do any two methods agree. Never do they all agree. Uranium-lead dating renders older dates than potassium-argon, which renders older dates than magnetic field decay, which renders older dates than biomolecular decay, which renders older dates than zircon-helium diffusion. A full 90% of all natural clocks render ages too young for evolution, but 90% of scientists are under the mistaken impression that it's the reverse. Remember that in the absence of constraints, entropy increases quickly like a popped balloon. It's diverse constraints that slow it down. So I believe our thinking about natural clocks has been wrong-headed. These inferences are maximum ages, not absolutes. I don't condone ignoring any science. All natural clock data should be welcomed, but as age limits, not as ages per se. And if we follow this logic, then it means that shorter time limits are controlling. For example, what if you unsealed an Egyptian tomb, opened the apparently sealed sarcophagus, and inside you found a wind-up clock, and it was still ticking? It would tell you something about your assumptions regarding the age of the tomb, would it not? Or consider another example. We know that a cup of hot coffee set on a table will cool off, so we might try to keep it hot longer by putting our hot coffee in a thermos bottle. If it's a good bottle, the coffee will stay hot until the next day. Most of the heat will be preserved. But would anyone expect to come back a year later and find hot coffee? Of course not. There's no way to preserve heat in a thermos that long. But effectively, what is happening is that evolutionist paleontologists are cutting into dinosaur fossils and finding a thermos bottle of piping hot coffee. Dinosaurs must have some way to keep coffee hot for 75 million years. Isn't that amazing? Amazing, all right. So what do we make of this? The second law of thermodynamics, coupled with the constraints of chemistry and repeated experiments, tell us that these huge and delicate molecules cannot possibly be even 1 million years old. Evolution has been saying that they must be tens, even hundreds of millions of years old. Some of us say that the fossil record must be much younger than we've been told, but evolutionists say that the fossils need to be millions of years old or evolution couldn't work. So the second law and the science surely must be wrong. I'll leave it to you to decide which to believe, but the evolutionists haven't been right about much of anything so far. That's what happens when one gives preference to imaginative storytelling over scientific law. Evolutionists have smugly asserted that theirs is the reigning paradigm, and that if anyone were to disprove evolution, such person would immediately win the Nobel Prize. However, neither I nor anyone else could ever aspire to such an honor because the job has already been done. By Ludwig Boltzmann in 1871 with his discovery that the second law of thermodynamics is also more fundamentally a law of statistical mechanics. Darwin never was his target, but Boltzmann dismantled Darwin nonetheless. The burden of proof is not upon others to disprove evolution, and never has been. The burden of proof is always upon the one making the claim. Increasing entropy is scientific law. So if you think natural selection can preserve anything, prove it. Increasing entropy is scientific law, so if you think there is an entropy transfer mechanism that can build a genome, prove it. Increasing entropy is scientific law, so if you think natural processes can spontaneously build huge, delicate biomolecules, prove it. Increasing entropy is scientific law, so if you think huge, delicate biomolecules can endure longer than 1 million years in fossils, prove it. Evolutionists have nothing, yet so many scientists persist in ignoring science. Folks, the second law is law. It is not an obscure or superficial argument against materialistic evolution. The second law is not esoteric and arcane. Rather, it's part of the mathematical fabric of reality. It is everywhere we look, and we are all dependent on it constantly, even if we are not aware of it. Every time you toss a salad or mix a can of paint, you're counting on it. Every time you breathe, you expect the carbon dioxide exhaled just in front of your face to rapidly mix with the outside air and for the oxygen to rapidly mix in with the air you're about to inhale. You see what I mean? The law works. Increasing mixed-upness is reality. It's why our cells die, but it's also why our cells could ever live. The energy of life is produced in the mitochondria in our cells, in which a probability gradient of protons across a membrane causes a flow of protons, implementing the second law that powers molecular turbine engines that mechanically forge the energy bonds in ATP molecules that can be carried throughout the body to release energy as needed, such as any time you move your arm or blink your eye. The second law makes all that work. We need the second law. Some creationists have suggested that the second law of thermodynamics was the curse which God established at the fall, but I strongly disagree. The second law is mathematical truth, and I believe math is a reflection of the character of God. He does not change. We very much need it to be true for our own survival. The law winds down what God winds up. The scripture says that in Him all things hold together. He upholds all things by the word of His power. Only He can make all things new. He is the one who gives us mercies that are new every morning. The curse is when God withholds some of His renewing power and allows decay to follow the math. The curse is not the math. Understanding the second law is the very reason materialists went looking for the beginning of the universe in some grand explosion, because the universe is observably randomizing with time, just as the law states. If we rewind time, we get to a beginning. That is very true. Yet a Big Bang is no solution at all, because bangs randomize things. They don't build things. There must be an ETM for the universe. I believe His name is Jesus.
Mercy's